outside of us. And they're really confounded in that conversation by two very different notions of scale, or two different ways in which scale becomes constructed. And what I want to grasp from Nigel Tufnell's line is where he says, we go up to 10, and when we need to kind of go over the cliff, we go to 11. It's that kind of pushing over the cliff to 11, where something very different happens, where you change scale, and something new emerges that I want to focus on. And for the Eames film, it's really that ability to constantly reframe. Sort of reframe at every power of 10 really provides a very different vantage, a different view. The problem looks different as you move across those different scales, and I'll borrow that later on in sort of articulating this method. But to get there first, I said I'd talk about sort of the phenomenological aspects of scale. And one of the things is that it's changing. Our perception of it is changing. And so this, there's an article about a year and a half ago in the New York Times about this. This is our, or was, our international standard for the kilogram. So underneath those three glass bell jars, you have actual, the physical measure of 1 kilogram that science has been using for quite some time. The problem is, like all matter, those entropy molecules start to come off, and the thing starts to weigh very differently. And so what had been a solid kilogram, a thing that you could measure everything by, is suddenly changing. It's no longer a standard, which means that all of you weigh a little bit more. But it also means that we have, as we've seen throughout history, whenever we've tried to create physical measures of scale, for example, an iron bar as a kind of 1 meter stick, the problem is that material over time disintegrates and erodes, and so it no longer is able to be as precise as it can be. So what scientists have done is they've changed the way to measure all that. And so they've decided that now, in the late 70s, they came up with a different way to measure a meter, which is the distance that light travels in a vacuum in 299,792,458 of a second. Okay? More precise, can be repeated. The problem is that it no longer bears any relationship to our physical body. So when you had the meter, which, over the different histories of measure, meters, foot, feet, whatever, were often in relation, say, to the emperor, the king's body, the physical body, the human body. This sense of scale and measure has now been changed to one that is completely unimaginable to the human and divorced, decoupled from the physical body. So we don't live in a vacuum. We can't experience a vacuum, and really can't experience 1/300 millionth of a second. It's beyond human perception. So the meter now, that used to be something that was deeply connected to the human body, is now something that's connected to a very abstract set of measures. And as we consider other ways in which our sort of built-in artificial environment is starting to reconstruct our relation to scale, I want to show you an interesting example, a couple of examples. This is a letter-sized document in Microsoft Word. And when I open it up as a letter size, so it's 8.5 by 11 inches, right? And so if I open that up on my computer, and I go to that little button right up here at the top, it says 100%. I get 100% of an 8.5 by 11 inch sheet of paper. So how big is that? If I measure it on my computer, it's actually 5.5 by 8 inches. So in this world that I'm operating in, that I spend a lot of time in, 6, 8, 10 hours a day, suddenly 100% of 8.5 by 11 inches is 5.5 by 8 inches. So this electronic environment has actually, again, decoupled my relationship to scale. I no longer have that same sort of physical, perceptual ability to kind of test scale against who I am and against the things that I know. Similarly, I'm sure many of you have worked in Photoshop. And so these two images, if you look at them on the screen, appear to be identical. But, as you may have guessed, the one on the left is 2.5 by 4 inches, and the one on the right is 50 by 80 inches. So when you print them out, they're vastly different in scale. So one is this big, and one is this big. But on the screen, they're identical. There is no difference between them. You can't distinguish really a difference between them. And if you've ever worked in Photoshop or almost any electronic desktop environment at a fairly large scale, one of the really interesting things that you find is as you're working at that scale and everything seems proportional on the screen, it looks really good, and then you print it out or tile it or do whatever to get it sort of large enough. You look at it, some of these things just don't look right. That relationship to scale has been completely sort of disfigured by this electronic environment where scale seems to float free of any real sense of measure. So in addition to this kind of troublesome relationship to scale at a perceptual level, we're also, I think, dealing with new kinds of scale at a conceptual level. So this is a piece that you're probably familiar with by Chris Jordan from a series called Writing Numbers. It's hard to see at this resolution, but it's a piece he constructed in Photoshop of roughly the number of plastic bottles consumed in the United States every 5 minutes. It's about 2 million. And it's a remarkable attempt on his part to actually try and come up with some way of giving almost kind of physical or some sort of perceptual form to the scale of an environmental problem. We all know about the kind of, or most of us know about, the sort of catastrophic change in our climate. But how do you get that? That's happening over such incremental and small degrees. Huge by sort of historical standards, but still to us, to have temperatures rise a degree over 100 years is not something we can really perceive. So here he's trying to give some physical form, although not physical, visual form, to the scale of a problem that we can't quite perceive otherwise, except as polar bears on floating little icebergs. And this was another example of a kind of complexity and scale issue where we have trouble wrapping our heads around what we're getting ourselves into. So this was a map that was produced by NATO, a diagram that was produced by NATO, more or less to sort of try and understand, come to grips with all of the different forces involved with the counterinsurgency effort in Afghanistan. So when General General Stanley McChrystal first saw this slide in a PowerPoint presentation, his response was, "We know we will have won the war when we understand the slide." In other words, it's so complex, and if the resolution were better, you could sort of dig. You can dig into some of these categories of, coalition experience and skill, visibility to the population, government security, corruption and tribal favoritism, Western affiliation backlash. It's all of this incredibly intertwined, networked, systemized levels. And this, this diagram could go on and on and on and on, deeper and deeper, more and more full of information of connected kinds of forces and counterforces. And so this level of complexity of dealing with what you do in Afghanistan almost goes beyond, as McChrystal was suggesting, it kind of goes beyond our understanding. We no longer understand the problems that we're trying to solve or address, or militarily subdue. Similarly, infographics were used in a kind of marvelous way by a sort of conservative infographics person, conservative political group, to try and sort of rally support against Obama's healthcare plan. And so what they did was they tried to show the kind of infinite, or near infinite bureaucratic tangle that Obama's healthcare plan was supposed to create, or they were claiming would create. And what's interesting is that there's some nice touches to this. So in the upper left it says, "Your new healthcare system," which is a wonderful kind of warm, inviting welcome. But what's the biggest thing? What has the largest presence? What's in the middle? What takes priority? What's bright red? It's the Secretary of Health and Human Services. So the point of this is to suggest that everything in your healthcare plan will be decided ultimately by a bureaucrat. So how you get your healthcare. So it's a very provocative and I think very clever use of infographics to actually make a sort of political point, even though I don't support a political point. But the larger idea here is that these systems have gotten out of control, that we can't really contain them anymore. They've gone beyond, whereas it used to be you seeing your doctor, and that was the system, and you could kind of understand that. You could get your mind, you could wrap your mind around that. It's now you are entering this system. And even if this is or isn't what Obamacare looks like, if you have much experience with insurance companies, healthcare, et cetera, you know the system is a little bit like this. So it is a highly complex system that doesn't make a lot of sense anymore. And I think these different kinds of sort of modalities, perceptual and conceptual. And next year I'm going to have a new chapter. I'm going to introduce timescales into this. And last year Ed Keller talked about timescales and got some new material by him as of this morning. If you want, there's a wonderful piece by an artist, Aram Bartol, that I think really captures kind of this interesting conflation of all these different perceptual and conceptual and temporal kind of interconnections of scale. So this is exactly how I see the city now. I see the city through Google Maps. And so this is a piece that's full scale. You can see it here. It's a piece, it's not a digital photograph, that's actually a sort of full scale piece in that little park. So what he's done is he's managed to kind of take our anxiety and our discomfort and our disorientation with scale and play with it. Give us a kind of a reading of how we're now starting to confuse sort of the digital and the physical, the immaterial and the material. And so as you move through the city, you are seeing, and when you compare this to kind of augmented reality, that when you kind of hold your phone up and you can see where Yelp shows you where your restaurants are, it's no different from this. This is kind of our experience, that these two ways of seeing the world are starting to commingle in interesting and provocative ways. Well, in order to understand scale a little bit better, and particularly in order to kind of understand some of the ways in which we can leverage scale to imagine kinds of change, I want to address this idea in science known as scalar variance. So there's an Austrian physicist named Fritz Benz who posed a kind of mental challenge decades ago. And he said, ants are relatively intelligent organisms, insects. And if we could shrink a book down to the size of an ant, could an ant learn to read? It's an interesting sort of problem. So if you shrink it down, and this is the lovely part about Google, if you need a picture of an ant reading, you can find a picture of an ant reading. So the question is, if you shrink a book down, can an ant learn to read? Ants themselves are not very intelligent. They're mostly all male. Don't know if there's a correlation there. But they're not very intelligent individually, but they're actually quite intelligent as kind of communal organisms, as hives, as nests. They are able to show quite adaptive and intelligent kinds of behavior over time. It's a fascinating thing. We'll get to that in a couple of weeks from the seminar for those in my class. So can an ant learn to read? Well, it turns out that the problem is that as you shrink a book down in size, the issue is not whether the ant is smart enough. The issue is as you shrink the book down to the size of an ant, the problem is the molecular bonds between the pages are too strong to actually turn the pages of a book scale to the size of an ant. And so as you move down in scale, the problem changes. It changes from one of can an ant read to one of molecular forces. Similarly, he said, can an ant take a shower? That one seems obvious. Of course an ant can take a shower, the water comes down, washes the ant, let it go. The problem is, as you move down in scale, that new forces come into play. The surface tension of the water, and you can see it through this slide, the surface tension of the water is actually too strong at the scale of an ant to actually wash an ant. Instead of sort of raining onto the ant, it bounces off of the ant. So ants clean themselves by rubbing themselves with their many little legs. And so surface tension at that scale, as you move down in scale, the problem starts to change, and that's what Fritz Benz was trying to get at, that with scalar variance, what happens at times is as you move and change scales, things can be quite regular, and then suddenly you'll get a change. And we know these are called phase transitions, if you remember any of your basic science. And there's some pretty simple ones. If you boil water, it's water. At 100 degrees, or let's say at 90 degrees centigrade, it's water. At 95 degrees centigrade, it's water. At 99 degrees centigrade, it's water. But at 100 degrees centigrade, it changes. It's now a gas, a vapor. So as you move along that scale, there's regularity until at some point, it doesn't go up to 101 degrees. It changes form. It changes property. Similarly, if you go down in temperature to 0 degrees centigrade, something goes from a liquid to a semi-solid. And this is, we can understand this. It's not so strange. I like to, this graph helps me to think about sort of linear relationships. The more is better. So I always use the example of a chocolate chip cookie. Chocolate chip cookie without any chocolate chips is not very good. You put more chocolate chips in, it's better. Putting more in, it's even better. The problem is, as you get to a certain point, you put too many chocolate chips in, and not any batter. The thing burns on the pan, it just melts into a chocolate puddle. You've changed the problem. It's no longer a cookie, it's now a burnt chocolate mess. Similarly, chocolate chip cookies are good. You eat a few, you feel good. You eat a lot, you feel sick. You eat too many, and you have an obesity epidemic. And so the problem changes from one of, does this cookie satisfy me, do I feel good, to suddenly I'm part of an obesity epidemic. The problem changes as you get more and more. And this is what I'm interested in with scale, is the idea that as you're moving along, and at certain points it's very regular, and then suddenly there's a shift from a linear to a nonlinear relationship. And that to me is the fascinating part about scale, that I think that we can leverage, and I want to give you some examples of these phase transitions. So the first one is less is different. So this is a typeface by Matthew Carter called Bell Centennial. He developed it for the 1976 bicentennial for the Bell telephone book. Now, the telephone book was this kind of thick book with lots of telephone numbers printed really small on cheap paper. Most of you may not have seen one. But it's, some of the challenges of printing is that you need to get a high density of type. You don't want to use many pages. You use a very low cost paper, so ink tends to smudge. And so if you look at a typical typeface, like Bell Centennial, at say 24 points, or 18, or 14, or 12, what you see is, as the typeface gets smaller, the type stays proportionally the same. Okay? But when you get down to 7 points, which I believe is what Matthew Carter was specifying for the telephone book, a new problem emerges. And that's that you have to account for the spread of ink on the page when printed on cheap paper. And so what type designers do is they create something called ink traps, which are these, which are just little divots, little cutouts in the letter form that actually accommodate and allow the ink to spread. They anticipate that ink is going to spread, and they account for them. So as you move down in scale to 7 points, in order to keep the letters legible, keep the counterforms and the open spaces legible, you actually have to reshape the letter and change. The problem changes because it becomes one of ink seeping. But there's an even more interesting example than that. And this is a typeface designed by a French type designer named Mathieu Huot-Marchand. And so he developed this typeface called Minuscule. And the idea here was that this could be read at 4, 3, 2-point type size, could be legible at that size, and would be both for the screen and for print. And this is, I believe, an example at 3 points. And you can see some similar sorts of sort of gestures and maneuvers that he does in order to make sure the typeface stays kind of open, that it's legible, and it's pretty effective. I can shrink it, and it's a very, very low resolution screen, but I can still kind of read it on my screen here. even the smallest type, or almost. And so the opening up of the letter forms, giving some space, kind of carving them open in strange ways, all very consistent with the kind of things that Matthew Carter was doing with Bell Centennial. But it gets much more interesting at 2 points. And here, the letters take on dynamically different form. They're radically different. But that's not even what I'm getting at. What I want to draw your attention to is the O in typograph, right here. You'll suddenly notice that the entire perceptual system has changed at 2-point type size. Normally, the stroke, the part you would make with a pen, is black, right? In the counterform, the empty space is white. But at 2 points, in order to make it legible, he's had to invert that perceptual relationship. We also understand that relationship as figure and ground, for those of you who studied art or design. In other words, before, black was figure, white was ground, if you look at all the other letters. But for the O, and actually as you look closer to the G as well, suddenly figure and ground have shifted right under your feet. And so 2-point type, it's not just that you have to sort of resculpt the letters, as Matthew Carter did, but it's that the entire perceptual system changes. And what's kind of amazing, I thought, what I love to do, is as you look at this, your mind can actually sort of put into and create around the O the stroke. It actually sort of sees the contour of that roundness around that square, black square. And so as the problem changes in scale, as the scale changes, the problem has changed to one of now having to shift the perceptual system. Let's take a different example. So let's say you're a movie maker, in this case Ridley Scott.